In this video, we're going to learn how to convert a fraction decimal number to binary in a single precision floating point representation. So for us to be able to do this, we are going to have to fill the following table. And in this table, there are three columns. The first column is what we call the sign. We have the sign column. And we have the second column, which is the exponent. Then the third column is where we have the mantissa. So for a single precision, there are 32 bits in a single precision. So the sign bit will have 1, the exponent will have 8, and the mantissa will have 23. So 1 plus 8 plus 23 is 32. So let us now do the conversion and fill up the floating point representation table. So the first thing we're going to do is convert the whole number part. The whole number part is the part that comes before the decimal point. So the first step is convert the whole number part. The whole number part, and the whole number part is 0. So of course, if you convert that to binary, you're going to get 0 base 2. So the next thing is to convert the decimal portion, that is the part after the decimal place. In our case, that is 0.025, 0.0625. So the next step is to convert the decimal. Let us use the word fraction. Convert the fraction portion. The fraction portion, and in this case, that part is 0.0625. So we convert this to binary by multiplying by 2 and noting the remainder. So 0.0625 times 2 will be 0.125, and the remainder is 0. Then we'll have 0.125 times 2. That is the same as 0.25. 0.25, and again the remainder is 0. The next will be 0.25 times 2, which will be 0.5, and the remainder is 0. Then we have 0.5 times 2, which is 1.0, and this time the remainder is 1. Then we read these values downwards, so that we have 0.0001 base 2. The next step would be to combine the two portions that you have converted. Remember, for the whole number, you had 0, and for the fraction portion, you had 0.0001 base 2. So combining these two, when you combine the two, you get 0.0001 base 2. So the next thing is to move the decimal point completely out of the number. But remember, the number you're dealing with was a small number, less than 1. So it means, therefore, that you're going to move to the right. So now, move the decimal point completely to the right. So we're moving to the right because the number that we were dealing with was less than 1. So the next thing you want to do is, as you move, you note the number of steps you take. The number of steps is what is going to guide us to get the exponent column for a single precision table. So now let us do the movement to the right. So you have 1, 2, 3, 4. So it takes 4 steps to move the decimal completely out. So the exponent is now represented by 4 steps. So now we convert 4 to binary, because remember our table is in terms of binary. So because it was to the left, this is equal to negative 4, because it was to the right. So the exponent is negative 4. So we convert this to binary. How do we do that? We take the positive 4. Remember, the positive 4 can be converted as follows. You're going to have 4 divided by 2, that is 2, and the remainder is 0. Then 2 divided by 2, that is 1, and the remainder is 0. And then 1 divided by 2, that is 0, remainder 1. And then you read these upwards so that you have 0, not 0, but you have 1, 0, 0, base 2. So that is the positive bit. So now you top this up before you convert it to negative. You top this up to 8 bits. So what you have is 1, 0, 0 base 2. But the column we are looking for requires 8 bits. So you have 1, 2, 3, then 4, 5, 6, 7, and 8. That is what we are going to use. But remember, it was a negative 4. So negative, you get the 2's complement. So get 2's complement to represent the negative number. So 2's complement you get by adding 1 to the 1's complement. So the 1's complement in this case will be 1, 1, 1, 1, 1, 0, 1, 1. 1's complement just involves the inversion of the sign. If you have a 0, you write 1. If you have 1, you write a 0. So it means, therefore, that the 2's complement of this would be 1. That is 1, 2, 3, 4, 5, 3, 4, 5, 0, 1, 1. Then you add 1 to that so that you're able to get the 2's complement. So 1 plus 1, that is 0, carry 1. Then 1 plus 1 is 0, carry 1. 1 plus 0 is 1. Then you have 1, 2, 3, 4, 5 is 2. So this is what we use for the exponent. 1, 2, 3, 4, 5, 6, 7, 8. So let us just take that straight to our table. So we can start by filling the sign bit. Remember, the sign bit just stands for the sign of the original number. Like in our case, the original number was positive, so that is represented by 0. And our exponent we have found to be 1, 2, 3, 4, 5, 6, 7, 8. That is what we have obtained according to our calculations for the exponent. Then now for the mantissa, you go back to the number that you obtained when you moved the decimal point completely out of the number. That is this portion. So when you did this, you are left with 1. So you take 1. That is what you write in the table. But remember, you have to represent the whole number portion. So what you're going to have, you're going to write this as 0, 1. This is what you take to the table. Remember, you have to represent the whole number portion that was there. So that's why you start with 0. Then you write the 1 that you have. But now this column requires 23 bits. So you're going to top this up with the rest of the numbers or the bits being zeros. So let us do that. So you have 1, 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And that is the floating point representation in a single position. Thank you for watching. Kindly remember to subscribe.